about the unbiased condition or the equilibrium state, at equilibrium state. So this is referred to as the equilibrium state p-n junction. So once again, what happened is that you have electrons, you have n-type and p-type materials connect to each other with a junction at x equals to 0. What happens that right at this contact, there will be a displacement of carriers. Therefore, because of this imbalance in carrier imbalance, you can look at the very important building potential. It's actually depending on carrier ratio. So if I have a p-n junction, if I look at my electrons, the electron ratio, the majority carrier electron and the minority carrier electron, the ratio between the two is identical for electrons and holes. The ratio between N and NP, PP and PN is actually the same. If you look at this, ND divided by this, ND divided by minority carrier concentration. So you have to have a sense as to whatever type of carriers you're referring to, it experiences the same. This suggests that it experiences the same diffusion force because the ratio between the two is the same. So it has experienced a diffusion force, and to counter this diffusion force, a VO is self-built, naturally built. So it's typically referred to as built-in. I should say built-in, right? Built-in potential. The built-in potential, what is the reason of this built-in potential is to counter this diffusion. To counter diffusion force, therefore, is proportional to the ratio between the two. That is why we get VO as KT over Q. Once again, counter the ratio of majority, hole against hole, electron against electron. And then finally, it will be, because we typically wanted to refer to the doping concentration on both sides, therefore, it finally becomes Ni squared, NAND, ln. This is within natural log. Okay? But the essential, if you want to capture the essence of this, is actually this. It's trying to counter the ratio between drift and, this is coming from because you're balancing two forces. So this is dP against mobility. So there's two type of forces, this weight between the forces, and it's to balance what you're setting up the imbalances. Originally there's an imbalance. How do you balance it out? The amount of balancing out depending on how much imbalance there is. If there's more imbalance, then you need higher building potential. So if both sides are more heavily doped, meaning that it's more imbalanced, then you will then need a higher voltage. So essentially the physics or the intuitive understanding of this is merely a force or barrier which counter the imbalance. The higher the imbalance, then you will then need higher voltage to counter the imbalance. And the imbalance coming from the ratio between carrier concentration, the same type of carrier concentration on both sides. Okay? Does that make it clear? Okay, so once we have this intuitive sense as what it is, we can do some exercise to find out, so what are the typical number of this built-in potential? So I'm just going to give an example and just to give you a sense as to what type of quizzes you should be able to answer, quiz question you should be able to answer. For example, if I'm giving you a Na, I believe it's 10 to the minus 16th. and ND. This is a very straightforward question. So find out. So this is very straightforward. What you do is that you just put in the number at typically will be given as a room temperature, KT over Q ln Ni squared Na Nd. So I'm simply just going to plug in the number, and a good number to remember, but it's typically given to you is about 2.2. Approximately 10 to the 20th. If you want a rough number for that, you're gonna just dump in the numbers. I just want to make sure that I got the answer correct. It's about, right. This is, as I said, this is 26 millivolt at 300 degree K. So if you dump in the number, you get a level about 0.7 volt. The typical building potential, I would say that this is referred to as a more lightly doped PN junction. This is on the lightly doped side. Lighter dope, I should say. If you have a highly doped, what do you expect it will go? So let me say that this is typically, you will see numbers between 0.6 to 0.9 volt. These are typical numbers. And there wouldn't be a large change because it's within the natural log, right? If you're dealing with this number at room temperature, because it's within natural log, therefore there's slightly up and downs between the two. So what are possible question if I give you this? So one is that I should say, what is the relationship between Xn and Xp? You should know. The next thing is that I'm not going to give you the answer. I'm just saying that if I give you something like this, you should figure out these particular results. And then what? Let me think Xn, Xp. And if Na increases, VO increase, decrease, or flat. So that sort of things. If I increase one side, what happen? Will it changes? Or let me think. What else? Lightly dope. Which one will be higher? I forgot. But that's sort of, you should be able to know that if I change certain parameters, how are the other parameters changes? Building potential, depletion. So this is the depletion width. Oh. And also maybe if both Na and Nd increases, how will your electric field at X equals to 0? Increase, decrease, or flat? How does the electric field inside it? This simply means that you have more imbalance if you dope it higher. So then your electric field should be higher. So this type of changes should have a sense as to all of the parameters, how does it changes with a condition variables. Okay? Okay, so so we basically cover what happens in at zero bias. One other things we want to talk about is that at zero, so first of all, you think about PN junction in three conditions. One is VD equals to 0 or no bias at equilibrium. And we typically refer to as at equilibrium state. So at equilibrium state, what you need to know, what are the key parameters that typically you will be asked to know. Of course, one is, first one A is built-in potential. The second is that color capacitance. And we're going to combine this with a discussion of under reverse bias. So I'm going to come back to this. But these are the two parameters when you have a PN junction under no bias or equilibrium state. So one of the key parameters is, it's called a junction capacitance. J0 stands for 0 is at equilibrium state. Okay, so the second part we're going to look at is if I'm adding VD, which is smaller than 0. This is called reverse bias. So VD is, so this will be smaller than 0, so this will be inverse applied. You can assume that the voltage you apply, VD, equals to a minus VR. So VR is by applying more positive which side? N side, right? So how does it affect your border? So this is like, we start with a natural border. So you have a initial difference between this diffusion, you set up this environment with a initial gradients difference or concentration difference on the two sides. And then the next thing is that what happened is that there's a built-in potential being built to balance out this imbalance. The next thing is that what if there is a external force which interferes with this balance? So this is an interference. Like I said, this is like Trump in office, which is he built a higher wall to preemptively prevent transport of carriers. So what it does is that if you think about it, I'm starting with a natural barrier. So still N on this side, P on this side. So this will be my Xn. This will be my Xp. Okay, so if I'm drawing V as a function of X, it will look something like this, right? Remember, start decaying right at the center, sharpest, and then it will flatten out. So this is your potential changes along X. And we know that the height is our built-in potential. So let me use a different color. Okay. So what happens if I'm trying to raise this bar even higher? So as I said, if I'm applying a VR, which is a reverse bias, it will be an add-on to your built-in. You already have a natural wall, but you want to add additional walls. It's the same direction because I'm applying more positive on the N side. Okay? So initially, there's already a barrier. Add on to so that you increase so with an increase of barrier. That is to say, I'm already saw with the V0, I'm stacking up a difference up by an VR. So therefore, if there's a reverse bias, if the green is VD equals to 0, and then the yellow will be something like this. It will be higher, the difference will be higher. And then the transition region will be wider down here. Okay? So what you can see is one key important thing is that your total barrier height, so the total barrier height will be from here to here. So your original barrier height is B0. Because I'm increasing, I'm adding, stacking up the barrier. Therefore, your total barrier height will become VO plus, it should be minus VD. And it's VO plus VR. If I'm dealing with a positive reverse bias, a biasing voltage. Okay? So one of the things is that how do you actually build more potential barrier? When we do this integration, you will see that if you look at the plot, VO is actually the size of this area. Size of this area, right? Because it's the integral of electric field. So this simply means that you will need to have a larger triangle, because the triangle area is the potential built up at this barrier. So if you want to build, for example, if you want to build a taller wall, you probably need a wider base. So this would then cause something called, what happens is that if I'm applying this, my depletion region will actually extend. So it would extend to a minus XNP, or probably here XP prom. So what happens is that if I'm drawing the electric field plot, so the original will be green, right? It looks something like this. It will be something like this. So this is my original, this area is original VO. If I'm applying more bias, it will become, so this is the original XN, XP. So to increase the area of the triangle, I had to extend it up. And one of the key things you need to remember is that the slope, what does the slope depend on? Do you know what the slope depends on? Anyone want to try? If you're coming from here, electric field is the integral of this. So there's integral. So this height will depend on the slope. The slope actually is proportional to the charge density. Okay, so this simply means that because I'm using the same material, there's no change in slope. I can only grow parallel. The slope is fixed. Let me use this. The slope is proportional to rho x at this particular region. Okay? I'm not giving the size, but just the slope. So that means that if I'm growing the triangle, it does not change shape. It's only changing parallel growth. Just so you get a sense as to what happened. So I just want to be sure you know that the slope does not change. So that if I'm extended to a XP prom, it will look something like this. I'm just exaggerating. Is it in parallel? This will be XN. There's a minus sign. This is a minus sign. So you then have an area, much larger area. The area in yellow will be the total area will be VA, VR. Okay? This will be, this actually equals to what? Let me tell you. It's exactly the area of the, because it's an integral, therefore it's xm prom plus xp prom plus Emax prom. If I'm highlighting this as Emax prom, it's just simply, if I have an ideal case, it would just simply be the area of the triangle. And this is also the same. So this will be Emax. There's a prom. So the original area, original integral will be 1/2 Emax. It's original Emax xn xp. Okay, so how much you grow in a triangle will be correspond to the voltage being applied, voltage being sustained, typically being sustained on this junction. Okay, so this is what happened in reverse bias condition. So if you think about it, what happened is that when you're applying a VR, you increase it. What happens is that you're actually creating a higher electric field. Your electric field is actually increased in the depletion region. But you will say that I'm actually having a reverse effect, but in depletion region. You will see that the electric field is generally being raised in the depletion region to sustain this voltage. But then what happened is that because of n equals to p approximately equals to 0, even though I have large electric field, because there's no carrier, therefore what happened is that you will actually see very, very low the amount of current. The current is essentially 0, even though with this raising of electric field, because of the depletion of carrier, there's no carriers inside, therefore there's no drift current. Okay? So essentially what happened is that during reverse bias, one of the key important observation is this. Let me use that. So if I have a dial and I'm sweeping this voltage from 0 to negative, let's say this is 0, and then I'm sweeping into maybe negative 10 volts, for example. So if I'm sweeping from 0 to negative to a large negative voltage, so what happened is that you will see that there's no current. I is essentially 0. There will be a very, very small leakage current. We're going to talk about that a little bit. But it will be essentially 0 when you operate it in reverse bias region. This is the reverse. This is I, D versus VD. And this is in reverse. Okay? So you will see something like this. Essentially, no current is being blocked. But as long as you're along this way, what happens is that you will then have a growth of depletion. So what happened? So how do you view this? This will then be viewed as, how do you model this, I would say. During reverse operation, we typically want to model this device with another circuit element. So it will actually look a lot more like a capacitor because it does not provide DC current flow. So ID, I should say DC current equals to 0 for a capacitor. And why can we view this as a capacitor? If you think about the structure is that you will have something like this. So let's say if this is under okay, so this is under equilibrium. So if this is VD equals to 0. So what happened is that under higher voltage, so if VD equals to minus VR, which VR is a positive number under reverse bias, you will see that the depletion region actually grow. So we define this as the depletion width, which is okay, the depletion width at equilibrium, which is Xn plus Xp. So if I'm applying reverse bias, what happened is that we already show that in our potential contours that it will grow. So it will grow wider like this. It would extend to minus Xn prom Xp, which will be higher. This will be Xn prom, larger than Xn, Xp prom, higher than Xp. It will grow on both sides. And then there will be more depletion on both sides. And one of the key important thing is that, I forgot to ask. One of the key important thing is that as we follow the skylines, your Xn and Xp will always be ratio Xn, Xp, or Xn. The amount of depletion is always the ratio between the two. Even though it would extend at the same rate, maintaining this ratio so that it will be charge neutral. So to maintain of charge neutrality, right? Because remember why this come about is that because these two areas has to net charge should be 0. These two should cancel each other. The area of this will always be identical to that, even though it's growing. Okay? Okay, so once it's grown, what happened is that if you think about charges or capacitance, one of the key capacitance is that we define a capacitance called, I don't know if you're familiar with call. We know that for large signal capacitance, the typical capacitance is Q over V. That's the total amount of charge. But in most of these devices, because it's a nonlinear capacitance, the amount of charge actually increases with potentials not linearly. So what happens is that we typically will look at something called the small signal capacitance, which is junction capacitance is a small signal capacitance, which is defined as dQ dV. But what does it mean? It means that if I'm changing the capacitance a little bit, how much does a change in charge happen? So if I'm at this particular biasing point, what happens is that if I'm changing my capacitance, if I'm making small little changes in delta V, so this is the corresponding dQ minus dQ. So meaning that if I'm applying a little change, for example, if I'm starting at this -5, I'm adding a delta V of maybe 1 millivolt. So I'm changing a little bit, increase a little bit of this voltage. It will then expand the depletion region a little wider. But the changes in charge will only correspond to at the edge of the already set up point. Okay? So what does it mean? This would then can be viewed, these small signal capacitance can be viewed as I misspelled it, as parallel plate capacitance. Everyone know how do you define the capacitance in a parallel plate capacitance, right? If I have a plate, so the plate is of an area of A, and then the key parameters, of course, the distance between the two and the material permittivity of this particular dielectric. So A is its area, D is distance between two plates, electrodes, and then this is the material dielectric permittivity. Okay? Right? So what is the capacitance once this is defined? C equals to what? Correct. So this is the unit area times this. So in our discussion, we typically use unit area capacitance, which is C over A. This is the unit area cap in the unit of farad per, for example, micrometer squared. In integrated circuit, we typically use micrometer squares or nanometer squares, but micrometer squares is very commonly used units. Okay? So we can actually do that for our capacitance across junction. So this will be, if you're following this guideline, the unit area capacitance, I'm just going to use the capacitance. This is once again unit area. It's called the unit area junction capacitance. That's all the junction capacitance. And it's typically in the unit of femtofarad. Once again, remind me what femto is. 10 to the minus, how much? 15, correct. So this is 10 to the minus 15. Remember, it's very, very small. And junction capacitance is especially small because it's depending on how much it depleted. So we're going to talk about that when we talk about other layers in integrated circuits. But anyway, we already know that the unit area capacitance, you can use parallel plate capacitance idea, so it should be silicon permittivity divided by the distance between the charge. So in that case, the distance between the charge will be the depletion width. Okay? Or another way to write this will be K permittivity of 0. This will be Xn plus Xp. If I'm applying a bias, my Xn and Xp will actually grow. Right? So from this is called K silicon. It's called a dielectric constant. it's at the level of 11 for silicon. It's a constant, and this is the permittivity in vacuum. The number is, if I remember correctly, you can go check. So this is the constant CM, I believe it's CM. You go check the number, but this is the primitive. This is a constant. This is a constant. Depending on dielectric, silicon and there's other material, for example, silicon dioxide, there are different dielectric constant, will give you different capacitance parameters. Okay? So what we found out is that you would, this would then give us an observation that as we increase our bias, so this is my biasing point, remember this is the VR. So if VR increases, what happens is that the depletion width will then increases. Therefore, we'll expect our junction capacitance will what? If I'm applying more bias, will increase or decrease? CJ? Decrease, correct. Because they're further away from each other. The further these two charges away, meaning that its unit area capacitance is actually smaller. Because they're further, the D increases. The distance between the charges increase. Therefore, your capacitance decreases. So let me see if I have any space. So I can actually give you the equation that, so you will see that the junction capacitance is actually, been trapped before. I'm trying to fix this. So what we can expect is, just from the understanding, is that your junction capacitance is inverse, let me write it down. So what happens is that if I'm drawing this as a function of VD, so this is 0. So at 0, if I'm considering only the reverse bias side, at 0 I will actually have the highest capacitance, which is referred to as CJ0. It's at equilibrium, and it will start to decay as this is the increase in, as VR increases, reverse bias increases. What happened? Okay? And then we can actually write it in a form of CJ0. Use CJ0 as a constant, and it will be inverse proportion to 1 plus VR V0. So this simply implies that as VR increases, in retrospect to your built-in potential, how many times higher, meaning that how your depletion with growth in respect to its real reference level, which is at equilibrium, and it will increase in a, it will actually decrease in a square law fashion. Okay? And I could also, and here, I'm just going to write something down. But then, this is just a reference. You don't need to actually remember it, just to give you a sense as to what it depends on. So its initial point, there's two things that would affect the capacitance of a junction. If you're considering, rather than the dependency of how much depletion growth as a result of reverse bias, if you're considering CJ0, which is at equilibrium, it will then depend on this. So what does this imply? It implies that if I'm having a highly doped, both of them increasing, what happens is that my CJ will then increase. The reason why, the background reasoning for that is that if I'm having a heavily doped junction, the depletion will actually be smaller. This will actually be smaller, will be narrower, therefore your depletion charge will be close to each other. The higher the doping, the lower you need to create the same amount of triangle. See, it will be sharper. So different type of triangle would affect how you actually, your junction looks like. So one of the key things in junction engineering, especially, we're going to talk about, not today, but next Tuesday, we're going to talk about how you actually, people spend a lot of time to ensure that how do you actually build a junction which will sustain high voltages. For example, nowadays people talk about third generation semiconductors. Those are for power operation, power applications. It requires sustained voltage up to 1,000 volts. So thinking about you need to build a tent, the triangle. How do you spread out the potential out in order not to have a very high electric field to sustain this voltage is a very, very important things in device engineering, especially in power device designs. So these are very key important. You want to keep it light, keep it flat, keep it extended so that you can still have the large area, but at a lower cost and critical field, that sort of it. So we're going to talk about this. What happens if you continue to apply bias next week? It will actually break down. So how do you make sure that it will sustain high enough voltage without breaking down? The key important, we're going to talk about circuits a little bit later, but you will think about a diode in two modes. One is that when it's forward bias, it's typically conducting current. So you want to know how much can it conduct. When it's reverse bias, the main purpose is to shut it off. So when you shut off, you want to make sure that it does shut off at all conditions. It does not break down when the pressure is too large. So a good switch should turn on and should provide high enough current when it turns on. And when it's shut up, it should be robust in order to endure high stresses. So how does a junction close to meet ideal specs, meaning that it's being stressed? Well, we're going to talk about that a little bit. So in terms of breakdown, a step from setting the current to zero, how robust can it endure the pressure or stress is a very key important parameters in diode designs. Okay? So I think we'll just stop here and then we're going to continue our discussion next Tuesday then.